learned. So let us turn our attention to the sphere of calibration. Okay. So I think I already have this loaded. There we go. Right. So we actually want to start partway through this. Right. Okay. So calibration, I'd like you to load in SIR agent-based calibration, okay, to get to this. In order to get to SIR agent-based calibration, you should go to example models under the help menu, and then you can just scroll down on the right-hand side here, and you'll find SIR agent-based calibration. You folks find it there? Sorry? Oh, okay. Yeah, I mean, I think that should actually be fine for purposes probably, but if there is an SIR agent-based calibration, that's great. Other people were able to find it? Okay. Good. So we're just going to be orienting ourselves with this. If I had time, I'd do it from scratch, but I don't have time. Okay. Right. I should have emphasized, and I apologize for not making this clear, but I just want to complete the loop. For this model that we just had, the parameter variation model, I do want to emphasize that while we varied only one parameter there, we could vary an arbitrary number, we could draw them from distributions instead of in some sort of regular way. There's a lot of richness that we didn't have time to explore for that parameter variation experiment. And I don't want you to think that the impoverishment of my example is an indication of AnyLogic's, a limitation of AnyLogic's functionality. In fact, quite the opposite. So for this parameter variation experiment, we could have, had, if we had more than one parameter, we could have included them there. We could have drawn this as a fixed value, but draw it from an expression that draws it from a distribution. In short, just be aware that there's a lot of power there, even if you build it up from scratch. Let's talk now, though, about calibration. So calibration within this model, this SIR agent-based calibration, you'll notice there's a calibration experiment. And I'd like you to go to it. At a conceptual level, there's a lot going on here that is very similar to what we've already seen for parameter variation. Specifically, you will see, if you go to the Advanced tab, a certain amount of similar sorts of mechanisms. What I want to highlight most particularly, ladies and gentlemen, is there is a very, very similar sort of issue where each simulation is run and then information is rescued from it. So we see exactly the same pattern here, that after each simulation model, it takes data out of the main object and it places it into a data set here. Okay. Now this data set is used somewhat differently. We'll get to that. But the point is, we have to salvage this data before main disappears forever. Main is going to go away. Mains come and they go, come and they go, come and they go. But the experiment itself, whether it's a parameter variation experiment or a calibration experiment, that persists. And hence we need to rescue data from each main before we toss it away. Okay. So that's an important difference. Let's go, or that's an important commonality. So we have actually a data set provided here under calibration, which retains this data, the data set infectious current. So we're going to actually read the data out of the model. This is a regular data set, and we've sucked it into our data set located in the experiment, and we're going to compare it. So let's go through the elements of this, okay? So if we go to this calibration experiment, let's go to general and start there. So what we see here is a couple of key things. Down at the bottom, there's a specification of what parameters are varied during the calibration. And we have these optimization stop conditions, which indicate how many different iterations are we going to perform within our optimization? How many different trial adjustments to make sure that we are that we're exploring the space well. So in this case, there's 500. We can have some automatic stop after the so-called objective function ceases to improve. In other words, after the discrepancy between our results and the historic data ceases to decrease significantly. So that's down at the bottom, working our way up. You'll notice there's this so-called objective here, and I'll just flash it up here. This objective, what this is saying is it's calling in a built-in AnyLogic function. You could define your own, which takes two data sets and compares them. And so it basically attempts to do a sum of squares type difference between two data sets, measuring the discrepancy between those data sets over all different time points. So here we have one data set that's a historic data set, and then we have another data set, DS infectious current. Does anyone recognize that name? Where did that name come from? DS infectious current. We actually saw that about 3 minutes ago. Sorry? It's a data set, and where did it come from? Where did the data that's in there, where did that come from? From whence did that come? Sorry? It came from Maine. That's right. And specifically, we rescued it from Maine at exactly this point, right here. Okay? So what we're doing is we're successively going and running Maine, sucking data out of it into this data set, the results that reflects the results of that model with whatever parameters we just ran it. We're storing it in this data set here, and then we're taking the difference between that, the discrepancy as computed by this function, a non-negative quantity computed by this function, the difference between that data from the model and the data historic, and we're trying to minimize that difference. So we're running this model many times. We're running Maine once, rescuing the data from it, taking the difference, and using that information, running it again with different parameters, taking the difference, etc. So we're trying to find the minimum such difference. And there's a lot of intelligence behind the OptQuest engine as to how it chooses the next set of parameters to try out. It'll take into account what are the best ones it's previously seen and maybe combine aspects of them, etc. So here we're trying to minimize those conditions, and you notice it's running Maine. By the way, you'll notice this reference to root here. That's our root. And in general, we could have many different possible roots. We might even have multiple, what we call sort of informally, multiple main classes that are each different structures of our model, and sometimes we might want to run it with one, sometimes with another, to examine the effects of different model structures. Okay, so we've just seen how that depends on the components we've seen. If we go to advanced, you'll notice down at the bottom there's a statement as to whether we allow parallel evaluations. This is actually a question about whether we are allowed to run several mains at the same time on different cores, okay, of our computer. And if I were to run this now, and I'll just do it in front of you, you don't have to do it, but you'll notice that it's actually using both my cores here. This is one core, this is another core, and it tries to keep them busy. It does what's called load balancing to try to make sure they're both well utilized. Okay, so those are some components of it. Let's talk a little bit more about what's going on here. This is this Euclidean distance function that we talked about, and you can go look it up, and here's this difference. And it operates on these two data sets, one historic, one from our own model. Now, we can define our own custom distance metric if we want, or our own custom discrepancies, and call off to it if we don't want to use Euclidean, for example. And again, we're specifying which parameters to vary and over what range. Here, we're defining a payoff function. How do we define the historic data in here? Well, if we go to the calibration experiment, what you'll find is there are a set of data sets that are provided. And in fact, they're located over here on the left-hand side. This DS infectious historic contains, is going to contain the historic value. Where does that come from? It comes from this infectious historic, which is a table function. So this is kind of like my answer to Roberto. Here you can have historic data defined in a table function, and then DS infectious current gets populated by that data. You'll notice right here. See that? Just at the initial infectious setup, I'm in advanced for the calibration, it fills this data set from this table function. So in other words, it creates a data set consisting of those same points that are illustrated in this table function here. So this table function defines the historic points, and then they are placed into this corresponding data set. And then how is that whoa! Oh my gosh. Okay, I'm not. Okay, thank goodness for a. Okay, good. And then that data set, where is that data set used? Where is this data set used? Who can tell me? DS infectious current. Sorry? It's used in difference, yeah. So the data set that we use in difference comes from this table function for the historic data set. For the data set from the model, where does that come from? That comes from, it's rescued from this main class that we ran, okay? Now, those are the key elements of what's going on. There's some other mechanisms going on here. So this is DS infectious current. Okay. Right. I should also talk about. Well, let me keep on talking about this. So this was populated historic data. Here we were retaining the data. Now, if the current iteration is the best so far, it actually saves away the data set, DS infectious current and DS infectious best. Where did DS infectious current come from? Where did this come from? DS infectious current, where did that come from? Sorry? It got rescued right here. This is the one from Maine that got rescued. And if it's the best one we've seen thus far, we save it away as DS infectious best to reflect the sort of best iteration we've seen. So if you're wondering, for example, where this is coming from, these red lines that show the best received thus far, the blue is there. There's the red. DS infection best is used there. Okay, so here within this graph, we're using the information of what's the best data set, yet obtained. Okay, so if we were to go look at this graph, what we'd see is DS infectious current is used in the blue, DS infectious best is the red, and DS infectious historic is the gold. That's how those are displayed there. This is the gold is the historic, the blue is the current, and the red, this is the best one thus far. Okay, so we have a lot going on there. Now, there's some additional components going on having to do with the presence of replications. So for each iteration of this Monte Carlo calibration, we're going to be running. We can run multiple replications. Okay, so here there's this replications tab, and you notice that it indicates yes, use replications. So what it's doing is it's doing many, many runs of the model. Here are just 5. It can do hundreds if required for a particular set of parameter values. And then it's taking the mean of those, okay? So in short, we have this notion of exploring parameter space that we went over a few days ago. So here we're doing calibration. We're finding the best combination of parameter values, particular points within this space that yield model results that most closely match historic data. And in order to assess a given point, because the model is stochastic, we run it several times. And what we see here is that under the calibration experiment, we're running it 5 times and taking the mean of them to make sure that we don't dismiss one of these points just because of a fluke, just because of a situation where it happened to, the stochastics made it not a very good fit, even though in general it is a good fit. So here we can run for a given set of parameter values. A given point here, we'll run the model 5 times. We may want to do it more than that, say 100 times. Or we may have it run a varying number of replications and it stops after a certain number of intervals once some statistical criteria is reached. And I explained that in my notes, the statistical criteria. So here we're going to have many runs going on, and it will actually take the mean of the discrepancy values across all those runs and use it as the sort of judgment for that particular combination of parameters. Okay, and I have some discussions of this whole process. Here we have a situation where we're running multiple replications, and I have some examples in here where you can print out results for the different replications, and explanations how it relates to behavior. Okay. Okay, I think that's all I'll present here on calibration, and refer to the online materials that I have. I have 2 lectures that I gave at MIT about this if anyone's interested. Yes. Yes. Yes, that's correct. Funny you ask. So at least in my version of AnyLogic, the terminology is not entirely consistent. But generally, we have an experiment that consists of a collection of simulations. Okay, and at the highest level. At the lowest level, we have replications going on. Here, 5 replications, okay, per simulation. Well, that simulation is with a particular set of parameter values, okay? This is the construct used for these experiments. However, in the documentation, sometimes these words are not used fully consistently. So you just don't expect perfect consistency with it. Yes. Yes. Okay. Right. Right. Here, as I was saying, there's inconsistency. Here, simulation is being used as replication. Okay, so after a given replication, it is actually rescuing the data, because replication involves one run of the model, right? So it's actually rescuing this data, putting it here. Okay, and it's actually running this difference for that on that particular data from that particular realization. And it's doing so for each successive realization of those 5, okay? It's running this discrepancy to figure out this discrepancy. And then what it's doing is it's actually taking the mean of those and using those for this get current iteration value. And if that's better than any others, it's actually gonna fill from a particular one of these. So this is this is what's going on, and simulation here is being used synonymously with replication, which is one of the inconsistencies. One way to verify your understanding of this, as I comment here, is to put in like a trace ln within the code to have it print out when it reaches a certain point, and you can verify this functionality. And actually, in several slides, I show how to do that and show results of that, which clearly demonstrate that this after simulation run is this code here, this handler, is being run for each successive realization within a given specific set of parameter values. So this set of terminology, which is adhered to by some of the documentation, is not necessarily reflected in the label of those fields. Okay, so that's a bit of a confusing thing. I would urge you to experiment with it and validate your understanding. Okay, so I hope there's a lot going on here. There's no question there's a lot going on. There's conceptual issues with calibration. There's issues with multiple replications. There's the terminology. There's the issues of just the mechanics, the plumbing of getting the data out. But I hope the high-level understanding will be maintained that in this case and in the parameter variation experiment, the distinguishing feature is that an experiment runs main many times and rescues data from each time to salvage the data and make use of it in judging the results and plotting out the results. Questions? Questions? Okay. I also have an exercise that I distributed to you, which will challenge you in terms of this, and I'm told by people who followed that exercise they understand this a lot better after doing that exercise. So you might consider that. Okay, it's on calibration. It's not trivial, but it's I think a worthy exercise that builds atop this example. Okay. Yeah. Yes. Yes. Yeah. 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 So this is a common issue. And it's one of the reasons why we use, for example, it's a motivation for markup chain Monte Carlo techniques where you're looking at the full posterior, because there may be many places with high likelihood of occurring, given the data available. So when you have this, it's kind of a form of ambiguity, right? You have many possible interpretations of what's going on with parameter values that yield all decent consistency with what you know empirically. And you know, in those cases, I'll often investigate what are the fundamental uncertainties. So we have some techniques. So I've used principal components analysis on this. Some colleagues of mine are working using latent class analysis, factor analysis for this purpose. But basically, what are the sort of it can be very helpful to understand what are the key sort of I'm going to use this term sort of components of that uncertainty. Like maybe it's something where either A is high and B is low, or B is high and A is low, or maybe it's that you know, so the A times B has to equal some value, or A plus B has to equal some value, or maybe A and B have to be high together or low together. It can be either one, but it can't be both. Right? So one could have in the data from the various well-fitting values, you could sometimes map those out and then do analysis on them to identify these patterns. So, as I mentioned, I use principal components analysis for this. It may not be the best tool, but in any case, those help you elicit high-level patterns, because often there's just a few key uncertainties, and you don't want to be overwhelmed by all these parameter values spat out. You want to look for the salient kind of differences among the ones that are all pretty good. And often a lot of things will be consistent, just a few things will be varying, and there'll often be irregularity in how they vary that tells you about its key uncertainties. Okay. Now, you may run all the results of those different successful calibrations in terms of the intervention outcomes you care about, for example, and find that maybe they all yield sort of similar outcomes of intervention A is better than the baseline, or intervention A is better than intervention B, or what have you. In which case, the sort of underlying angst of having multiple possible interpretations is greatly lessened, because well, I don't know what the situation is, but exactly with the parameter values, but they're all pretty consistent in terms of things I care about, which is in terms of the intervention outcomes, right? And sometimes that's the case. Sometimes that's not the case. And then the plot thickens. And sometimes what you'll find is the uncertainties are such in terms of the systematic variation associated with them that what you really want to do is try your best to resolve some of that uncertainty. For example, trying to pin down one of those values, trying to get any sort of data that would shed light. Is A high or is B high? Something that will let you pin down that uncertainty, and that's in advance. I mean, it's not merely we're thrown back into the parameterization phase, thrown back on our back, and and have to struggle. We've actually learned something. We've learned about a few key salient uncertainties, and that allows us to focus on them and try our best to get information about those, because we know those are important. They are key uncertainties about the model, and they make a big difference for the intervention trade-offs. Again, if it doesn't make a big difference in intervention trade-offs, I don't know if it's worth all your time. But if it does, that's something you can focus on then and try to drive it forward. And we've done that in our model. It's a good exercise, and eventually you should aspire to get a feel for what are its key uncertainties. Where's the wiggle room? Where's the wiggle room in there? Because that lets you sort of approach the calibration more artfully. You may be able to combine certain parameters. This is a common thing. If you're constantly using certain parameters together, in mathematical epidemiology, beta times C, for example, you don't have a lot constraining the particular values for them, and you might want to treat them together as one parameter. In a dimensionality analysis, a formal dimensionality analysis can sometimes eliminate several parameters, thereby eliminating some of these calibration woes. Okay, so I'm glad to talk more about that offline. Okay, right. Yes. Okay. Yeah, and I have some suggestions here on sort of rules of thumb for approaching calibration. Spent a lot of time doing that, and so gotten some good experience. Okay, so what I'd like to do now is to continue on sort of our grab bag of topics. So we've done these two, and we're going to have to finish in about 20 minutes. So I'm in extreme extreme sort of triage mode here. Okay, maybe what I'll say is, right, I had some slides on building user interfaces for models, and I don't have a lot to say about this, so I think I could whip through this quickly. I have some exercises here that that build on previous models. I wanna highlight the fact that AnyLogic in its palette provides a very rich set of so-called controls. And you'll see them down here, controls. It also provides these things under presentation, like text and so on. These are very powerful. You can set their properties for things like the label, or for things like a line. Remember, we set properties of a line to have it go over a certain amount and down a certain amount, and all those sort of good things. So over here, there's a set of ways you could craft the user interface, but these controls are ways of capturing user input, and are also customizable. So you could set up buttons, you could set up checkboxes, edit boxes, radio buttons, sliders, etc. We've already seen some ways of capturing user input when you click on a node in a graph, in a node in a network diagram. To be less ambiguous, you could do things. Remember that? We could click on a node in the network diagram, and we could, for example, have it print out some information or along those lines. I think we may even have had an example of where we sort of sculpted the network. So, for example, if I wanted to be able to click on a node and have it delete that node, where would I go here? Remind me? This is another pop quiz. Where would I go? If I wanted, in this model, this minimalist network ABM model, to be able to click on a node and have that person disappear from the model, where would I go? To the oval associated with person. I think it's a wonderful sign that I hear so many voices. That's just great. So I go to the oval, then where do I go? Dynamic. And then where do I go here? On click. And what would I put? Okay, yeah. You've got, okay, this dot get underbar main. Then remove population of this. Yeah. Why this here? Why is this? It's me. It's me. It's saying remove me. I'm just so happy. It makes me so, it gives me no small sorts of pleasure to hear people talking and suggesting these things. So I click now, and now we can have people be deleted. Now if I did apply network after, you'll notice there's a bit of a lag. See that? They disappear before their connections. See that? If we wanted to have the connections disappear at the same time, anyone want to know what we'd do? What would we do? Yeah, you apply the network. Exactly. So we could say, hey, go reapply the network immediately. And how would we reapply the network? That's something we ask of who? Who maintains the network? The environment. Environment dot apply network. Boom. Right? And so then we can go run this. And so this is an example of a user interface component. Alternatively, an aspect of user interface. Alternatively, let's suppose we wanted to add a person when we clicked a button. How do we do that? Well, we drag in a button. You folks haven't really seen this before. We saw it with a slider. Remember that? Okay. When you have a button, I'll say add. I'll call it a button add person, and this will be labeled add person. And then I'll make it enable true, so it's just constantly enabled. That's actually optional. But what do I do here? Okay, but this is actually in main, so. Yeah, so this dot population dot oh gosh, I thought it was add population. So ooh gosh, I'm toning out for a bit here. Yeah, population dot no Oh, yeah, maybe that's kind of, oh, yeah, of course. Sorry, folks. Long day. Add underbar population. It's a property of main. This is something added dynamically to main as a method of main. It's actually not something I ask of the environment. It's not something I ask of the population. It's something I ask of main. Okay, so add population. I add a population member with default attributes, and then I could run this. And so that was in the action of the button. And so now, I can go add people in, right, when I click this button. And in general, I can add many types of UIs. By the way, I'm not having them apply the network. If I want to do that, I just have to do the apply network as well. Environment, this dot environment dot apply network, right? So these controls are very powerful. We're only touching the surface. Some of the more sophisticated ones, you're going to actually need data to populate it of some sort. So here people are being woven into the network. But like things like the radio buttons or the list boxes or the combo boxes, you're going to need some data to say, like, what do you want to choose between, for example. But they're very powerful, and they allow the creation of rich interfaces. Sliders can set the values of things, etc. And to be clear, these things can be put in main. They can be put in a person level. They can be put in the experiment to set the initial parameters. You can kind of choose where you'd like them to live. They're very effective ways of building up rich user interfaces together with the visualization we've already seen. So here we have a set of these controls that provide us with mechanisms. And I have some little exercises here that will put you through that have you create sliders to set parameters for the whole model, etc. Okay, so you may want to follow that. That's building user interfaces for models, okay? Triaging right along, that was sort of output. Debugging. Let's talk a little bit about debugging in AnyLogic. So we've used a variety of techniques for debugging over the years in our various models, and in many areas of this bootcamp we've been talking about have we built the right model and model conceptualization, but here we're asking often about have we built the model right. One of the things that makes it really, really difficult to understand is that, or to assess, is that that frequently unexpected behavior is associated with emergence. We see some unexpected behavior, surprising behavior. That can be the hallmark of emergence, but it also can be a sign of a bug. And this is why we typically try to build up a model very incrementally. One of the key reasons to try to spot when something unusual emerges, we know, and we've localized as much as possible where it's come from, because we know there's just a small difference from the last version of the model. If it's just appeared now, we have a better chance of tracking it down. And that could be tracking down to a bug, or it could be tracking down to some very curious form of emergence. So one of the challenges of us working in the complex systems area is that it's sometimes hard to distinguish between these. Right. So types of oversights can occur at the design level. You implemented what you wanted to implement, but it had a problem in it that you didn't realize. You neglected some case, like a case where the population is empty or something like that, a case where there's no infectives. And your model works great in general, but then it breaks down for that case. Or it could be a situation where you said something you didn't mean to say, or where it interpreted in a way you didn't want to interpret. For example, you type A over A plus B. What you really meant is this, but it interprets as A over A, 1, plus B. That's quite possible. So debugging is the process of finding and removing defects from our programs based on observations of failures or aberrant behavior. I have a whole lot good lecture of this online. I think several versions of it. Suffice it to say that one of your goals is to make your model, if it has bugs, make them reveal it themselves as soon as possible. If there's a problem, you want to know it as quickly as possible. Just like you want to know if there's a problem on your airplane before you take off. So you want to fail early. You want your model to alert you to problems. And one of the best ways to do that is to use assertions in your model, that these things will basically encode your assumptions. The time is too short for me to go into this, but I provide a variety of debugging options for AnyLogic here. I should note that AnyLogic's researcher and professional versions, if I've gotten the terminology for them right, they contain a rich debugger. It's very, very powerful. It allows you to set debug sort of breakpoints, things called breakpoint. If I say breakpoint, how many people know what I mean? Okay, not everyone, but the idea of a breakpoint is you can get the model to stop at certain parts in the middle of operation that are of interest to you. Okay? You can get it to stop, for example, when a certain event goes off. You can get it to stop just as it's starting up. You can get it to stop whenever a message is sent, something along those lines. And the AnyLogic debugger provides a way of doing this. It turns out you can also attach to AnyLogic from debuggers such as the Eclipse debugger, but you're dealing with things at a lower level. You don't have the option of simply setting a breakpoint on a event, for example. You can set it on some code that corresponds to the event, but it requires comfort with working with some underlying code more. But you could see all the code. You can look at variables in the code, see what the person's current state is, and so on. It's just it's not nearly as high a level as the AnyLogic debugger provides you the option of. So it's kind of a poor man's version of debugging. However, some of the best ways of debugging, so Kernahan and Ritchie, two of the pioneers in programming languages, creator of the C language, which has spawned eventually Java as a member of the C family of languages. They commented they only use debuggers for really, really difficult bugs or for unusual occasions. You can get a lot out of manual tracing and reporting, the sort of trace LN that we've been doing. When something's going wrong, just printing out things that lead up to that point, and you can get a fair bit of understanding. It's a little bit labor intensive. It requires you to often go back and take those things out. There's some more sophisticated ways based on techniques known as aspect-oriented programming, for whom that's a familiar concept, where, for example, you could instrument the model so that all transitions print out messages to indicate they're occurring without you having to go mark them up. That is, you just have one line at the right place and it says all transitions print out messages when they're firing. But that's a fairly advanced topic. In general, the trace LN that we've been looking at is very powerful, and it can let you track down problems. There's also tools, logging tools like Log4j, which allow you to enable and disable logging for your model in a very flexible way. So you run the model now with no logging, and then it starts exhibiting problems just by changing a file. Without changing the model at all. By changing one line in file, you can have it print out vastly more information about what's going on. This is a very powerful technique. It's known as logging, and this tool, Log4j, logging for Java, allows this very customizable logging. It can put it out to a file. It can put it out to a database. It can put it out to all sorts of places. I have videos that show me attaching the AnyLogic debugger to, the Eclipse debugger to an AnyLogic model. Again, depends a certain degree of comfort with looking at the code. The AnyLogic Professional Research Debugger is a fantastic tool if you can get the appropriate license in place. It's a really great tool. So if you want to output things manually, you want to do manual tracing, this is a very lightweight way to do it. It requires markup. So you have to go insert statements like print this, trace ln of this, trace ln of that. And it can require sort of many runs of the model till you really zero in on what it is, what's going on. You can use this system.error.println. Instead of doing trace ln, you can do this and it will appear in red, which is sometimes helpful. So for example, when someone, if there's a message cure, we may deliver a message to a person and then print out, I sent a message to this certain person. And that may help us understand what's going on in the model. You can sometimes set up these mechanisms like buttons and sliders and so on to help us set values for use during simulation while you're trying to debug. So for example, when you press a button, it will report some information that's of interest to you to figure out what's going on. I'd refer you to a model, ABM model with birth-death, which uses some particular features, which shows a lot of demographics and so on. It shows a lot of accumulation of information. And one of the things that I do is I show how you can like click on an element and have it do some custom reporting. So for example, maybe when we click on a person's circle, we have it print out their information on their children, something along those lines. So I have information here on log4j, different levels of debugging that it provides, and how you can switch between logging levels using config files. These are just files. You change one line, and you can have it go from printing out nothing to printing out a huge amount of information about what's going on with your model. This is the external debugger. I don't have time to go into this, but fundamentally you can attach to a running AnyLogic model. Okay, debugging in AnyLogic is a significant topic. I teach a little bit of debugging in my software engineering classes. It is a topic which is an art. It's an art to learn how to debug, and a lot of it is about simplifying the problem. If I had one single suggestion for you for debugging, it would be make a backup copy of your model and rip pieces out until the problem either disappears or until you get down to a level where there's only one possible place it can live. Make a copy of your model first, because you're going to be ripping it apart. This is a tried and true technique. Often you can rip whole sections of your model out, and then you get more and more localized in where the bug could be. There's some problem, maybe it's a null pointer. Maybe it's a stack overflow. Maybe it's a problem with it tells you that it can't send a message to the bird. It can't connect to yourself. It's some message you don't fully understand. Make the copy and start removing pieces of it. And each successive piece you remove, if the problem's still there, now you've got less of a haystack to be looking for. It's less of a haystack to find it in. If the problem disappears, that is a big hint. Often it indicates that the problem is associated with that part you just removed. So it gives you a great hint as to where it might be. It's like having a metal detector over the haystack. You throw out tuft of hay after tuft of hay. The metal detector is still squealing away. And at some point you throw out that tuft of hay, and the metal detector stops squealing. That tuft of hay you just threw out is probably where the needle is. So it is with debugging. And I would urge you to, think carefully about where the problem might be, artfully strip away things, and see if the problem goes away or if you suddenly realize what it is. Okay, and of course, have someone else do it. I have a whole set of best practices, which I would dearly love to talk with you about. But time is unfortunately a fleeting, and I think we're going to have to stop. Is that right, Tim? Yeah. Please, I would suggest you look at my best practices videos. I talk about things like pair modeling. This is one of the greatest things. You take the most advanced modeler and sit them down for someone who's new to modeling, and the advanced modeler will do much better with that person next. You take the beginner of modeling sitting down next to someone who's at their same level, they will do much better with that person sitting next to them. That person will help spot silly mistakes. They'll help spot oversight. They'll provide a different way of thinking about it. They'll build both a better model and a model that's more likely to be correct up front. This is a tried and true technique in software engineering, and it's the most simple form of peer review that you can do. You can put your trust in it. Okay, I have lots of other recommendations from peer review to using version control, to using assertions, etc. I would strongly suggest you take a look at those videos. The time will be well rewarded, I think. You will save well more than the time you spend watching the video. So if you can do that, if you can stomach it, I think you'll benefit from it. Okay. I wish I could talk more, but alas, this is all. And we'll have, I think, a break and then a reflection session on the week and some additional opportunities for discussion. Thanks very much. Unexpected. Thank you kindly.